Hey, John here. This is part 2 of a sequence of videos where I walk through the creation of Verilog implementations for finite state machines. As always, a big thanks to all my supporters, especially my Patreon VIPs. Now let's look at what we call a message recognizer. As I point out in here, by the way, this handout here I made for a course that I taught some years ago that I just updated. You can see this date right there. That's 2 days ago from when I'm recording. I added some cause-effect arrows to the waveforms and some other things. If you haven't gotten the latest, greatest copy, you can run over to my old faculty page. I did update the link over here. As you can see, I put this date in there. My previous management allowed me to update that site still, even though I don't work there anymore. Students still use it, so why not? It's good for everybody. All right, I'll put links to this stuff below in the description on YouTube. So what do? I point out in this paragraph up here that, as last time we were talking about just simple counting. You got a clock that ticks, and you pick an edge. I believe the examples I chose last time were leading edge sensitive clocks, and every time there was a leading edge, we counted. What does it count? We add 1 to the current state of the system. In this case, a more general state machine, what if we simply, generalize this beyond counting in order? Now, the way I think about a state machine that's built the way I'm going to show you this one, this is not a one-hot. I'd mentioned that in a previous video. We'll get back to there eventually with a more interesting example at some point. But the implementation we'll look at today is going to have 2 always blocks, and what we're going to do is we're going to store the current state value, as shown in this state table down here, as a multi-bit binary number, just like we did when we were simply counting. The difference here is we're not going to count in order. Okay? We're going to use the state to represent history. You would argue that the counter represents history. What's the current count value? Well, it's the number of counts that happened before now. Modulo the number of bits in your counter, of course. But that's really what it represents. Where am I in the evolution of history is one way to think about what it means for this for the definition of this current state variable. All right? And in this case, we're not going to count in order. As you can see, we're going to see, what do we got? Here's a state 2. The next state here is 1, for example. Here's a state 2. The next state's 3. You can argue that's counting. Here's the next, the current state is 3, right? 1, 1. And the next state is going to be 1. So we're not counting just 0, 1, 2, 3 anymore. And I want to punch this right now because we're not just simply going to put an adder in our circuit and add 1 to the state every time a clock ticks. What we're going to do is we are literally going to look at the current state with a combinational circuit. We're going to look at the input. And we're going to cough up a next state number that's arbitrary. It's kind of subtle, but it's more generalized. A message recognizer. Let's make sure we understand what that is. I think of this as a little, a small UART-like thing, although it's not asynchronous. This example is synchronous, so it's a USRT, I guess. The idea is that we're looking at a value that I'm going to supply the circuit in a signal called D. That's my input. I'm going to look at what the value is over the course of time. And I want to know if I saw a 0 followed by a 1 followed by a 1. Has the circuit recognized that it saw a 0, 1, 1? And if it does see that over the course of time, it'll assert a 1 on an output signal, Q, the output of my state machine here, for 1 clock period. So that, boils down to how do we define time? Well, in this example, we have a synchronous input, and we're going to sample, we say, the D input on each one of the falling edges of, in this case, a free running clock, which is very common. A lot of state machines will have a free running clock. More often than not, that's what you're going to find, okay? So this thing will be free running. Every time we see a falling edge, we're going to look at D and say, oh, have I seen, one of these bit values? If I see a 0 right now, I'm like, okay, maybe if I see 2 more 1s, not maybe, definitely, if I see in the next 2 falling clock edges, a 1 and then another 1, I will, at that point in the future, have seen a 0, 1, 1. That's what this is doing. I'll clock in a 0, clock in a 1, clock in the second 1. At that point, I have seen, or will have seen this thing, and I assert Q for 1 clock period, and then Q goes back to 0 again. So that's what we have the Q over here. We say if the current state is this, the input is a 1 or a 0, the next state shall be that, and we look it up in this state table. And I rarely use state tables when I go through this. I rarely work out all the sum of products. This is more of an academic handout. I usually go right for the waveform diagram right here and say what happens over the course of time. And then I backtrack and figure out my state stuff from there and work into here. If I build the circuit discretely, I might use this technique, or I might just put a decoder in there, which, as you may recall, generates a single output for each one of the products that you could ever have, given your set of inputs. And in this case, there would be 3 at that point in the circuit, right? I would use an LS138 and then just put some OR gates on there. And I show that in a video in my class lectures down here. If we go back to, where are we? This right here. If you watch this, that's what I do. I scribble it out by hand, and I know I make a mistake in there. Read the description below this video. I should probably re-record that at some point. Let me know what you think in the comments of that other video, and I'll collect them up, and maybe I'll redo it someday. Anyway, my point is, I usually go right for this stuff and then come back and work on the circuitry, or I can just implement Verilog directly out of here. It depends on how much you can do in your head. For a college student, they have to be able to do all these things, right? You have to have experienced it in order to know when you use it and when it's simple enough to do in your head. It's as simple as that. Okay, let's look at the waveform here. Clearly, here's my output Q. It has been asserted at this point here for 1 clock period from falling edge to falling edge. So it must have recognized our input, which you recall is a 0, 1, 1. Over the course of time defined by these falling clock edges. In other words, there's a falling edge, it saw a 0 here. Falling edge, it sees a 1. Another falling edge, it sees a 1. So therefore, at this point in time, we can say it has seen a 0, followed by a 1, followed by a 1. Now, I added this arrow, part of what I edited the other day, to indicate the fact that this thing rises here solely because the clock ticks. All right, this is a Moore-based state machine. So Q is defined solely based on the state, and the state changes because the clock tick. I suppose I should have shown cause-effect arrows in here. I'm open to some debate and discussion on this. If you think I should redraw these at some point to better illustrate what's going on to a student, if you've already seen some of these, know a little bit about it, let me know. I mean, I go back and forth on should I do this, should I not, how should I express that? Right now, I kept it relatively clear. I just said the falling edge here is what causes a sequence of events to take place that results in Q going high. Okay, so and that's what we're looking at in terms of the idea of sampling, right? Let's look at a state diagram here. This is Moore, so you see the input current state right there. You see that the state generates the current Q output value, and the D input is on these arrows here. So if I'm wake up out of nowhere. What I'm really, this state over here represents I'm waiting to see a first 0 in the sequence. If I get a 1 at that point in time, I cannot possibly be ingesting the 3-bit sequence yet. You can clearly see if I got a 0, this state diagram represents the fact that this 0 advances me towards my goal, which is over here, by the way. As you can see, the output is a 1 in that state over there. Foreshadowing. Spoiler alert. All right, so in state 1 here, what this bubble represents, what it means, is I have seen a 0 that might be part of the message I'm looking for. Have I seen the whole message yet? No. So I'll put a 0. I didn't see it, but I'm working my way through. Working my way back to you, babe. Right? Okay, so I'm going to just call that state 1. If I see a 0 in that state, what does it really mean? Right? Well, it means that I did see a 0 that could have been part of a message, but I just see another 0 right now. That 0 that I saw that took me over here that brought me into state 1 in the first place cannot possibly be part of a message that is 0 followed by 1 followed by a 1. It just can't be done because I just saw another 0. So therefore, this new 0 might be the 0 that's part of a message. In fact, in this diagram up here, the first 0, if we look at this state diagram down here, could be very well defined as the one over here. Is that part of the 0, 1, 1? No. If I get another 0, look at the state up here. I'm in state 0, and that's really what these numbers up here represent, is what one of the bubbles I'm in over here. If I'm in state 0 and I see a 0, what am I supposed to do? Well, I go over to state 1. You'll notice it changed from 0 to a 1 right there. And that happens on the falling edge of this clock, okay? In a more base state machine, everything happens. As a result, everything on the outputs, or the state itself, I should say, happens as a result of the falling edge of this clock. The only thing that's not necessarily controlled by the falling edge of this clock is D. Okay, this is our external input. Everything in a Moore machine is based on that falling edge. Okay, so the state goes from 0 to 1 because it saw a 0 on the D. That's this guy right there. What is it supposed to do? It's supposed to output a 0 because it didn't yet see one, and that's my cue. It stays 0 right there. Okay, if the second time the clock ticks I still see a 0, I'm going to stay in state 1 because this new 0 might be part, in fact it is, as we can see here, might be part of a 3-bit 011 sequence that it wants to recognize. So this means here that I have seen the first 0 that could be part of a message. All right. If I then see a 1, I'm all excited now because I saw a 0 to get into this state, and 1 means go over to state 2 over here, which represents the fact that I have seen a 0 followed by a 1, and I'm working my way towards the recognizing of this 3-bit message. I haven't seen it yet, so the output's still 0. That represents right here. Okay? So I saw a 0, I saw a 1. I go into state number 2 from state number 1, which we see in the waveform up here. Right? So here's state 1, here's state 2. I saw the 1, I come over here. Okay? If at that point I see a 0, well, then clearly I didn't get the whole thing. I got a 0 and a 1 followed by another 0 in that definition. I'm going to go back over here. I don't go back over here because what happens is that 0 that I just saw might be a new message. So I can't throw it away. I can't go all the way back over here, all right? Because this one represents I just saw a 0 that might be part of a message. All right. In this example up here, the next time the clock ticks, there is a 1 on D. Aha! And I'm in state 2. What do? I go over here to state 3. And now I start outputting a 1 because I'm in a state that says I saw a 0 followed by 1, followed by 1. This guy's high because I'm in state 3. At that point, if I see a 0, it might be part of a new message. I come over here and I start going around. You can see that's state 1 and so on, right? If I see a 1 on the input, I warp way back over here because I'm seeing junk data that cannot be part of a message. That's what this state over here means. and then I need to see a 0 before I start thinking I'm seeing this 0, 1, 1, and the 0 brings me back to here. All right, that's a little bit of a review. I probably should edit this out, but just to get us all back up to speed on what a recognizer actually means. This is also part of the Wonder lecture that I do in my course over here. All right. All right, so this is an example of the state machine working and recognizing its inputs. So let's go ahead and look at how we do this in Verilog. And the way I think about it in Verilog is I'm going to simply create all these states. I'm looking at my D, and I got these falling edges of the clock. There should be an overwhelming sense of an always block with a neg edge on the clock, and looking at the D variable here in a combinational circuit that decides whether or not I'm moving around between my states. How do I determine whether I'm going into state 1, state 2, and 3, and so on? So this is the third example in the repo I'll link to below in the description on YouTube. So let's look at our state machine here. Here's some more links on what's going on. This is not true anymore. I moved that into a repo of its own. See the links in the description below this video. Okay, what do we got here? I'm going to create a finite state machine module. The same as the last one, very similar anyway. We got a clock. This one's going to allow us to reset it at any time. The handout does not talk about that, but in this case I do have this signal. We talked about that in the last video. Our data input is a wire, and it is synchronous. It is synchronized to the system clock. And the output is also going to be a wire, because we're going to generate this in a combinational circuit somewhere, and we're going to assign it to Q when the state is a 3. Okay, we have a next state that we're going to calculate as the output of our combinational circuit down here. We have the current state in sreg. We have an always block that represents the latch or the flip-flop of our circuit in our more state machine. We talked about this last time. If the clock has an active edge while reset is on, I simply reset my state to the beginning state, which is 0, as I defined in this diagram down here. I said, oh, if you ever reset or wake up out of nowhere, when you first boot up, you're in state 0, waiting for the first 0 in the sequence. That's good. That's what that does. And down here we say otherwise, it's not reset, and the clock ticks. Simply take the next state that's calculated down here and put it in our latch. Okay, just like the counter. Now, here's how we calculate the next state value. We talked about assigning these to XX don't care values, and the value of that, the usefulness of that in simulation, so you can help debug your code if you forget to make an assignment down here somewhere. In all cases, no pun intended, when the data is input is high or low, I'm assigning the S next value in here. If I did not do that, it would end up being assigned this XX. If I left this out and missed one of these, then I would end up with an inferred latch, which I would anyway, because remember that the case statement, if sreg has X's or Z's in it, and I don't match any of these, I'm missing a default down there. So this is a lot like having a default. You might ask, why don't we just do that in a default? As a recap, we don't do that because I could also leave one out like right here, in which case this would not get assigned even if I had a default down here, because by definition I would be in this particular case item, and if I don't handle all the possible situations, I end up with an inferred latch. So this gets rid of all the possibilities of an inferred latch, saying I definitively don't care what you put in here, and simulation would make it red and put X's on there. If we look at the waveform diagram, okay? So let's look at this. If I'm in state 0, D is high, I stay in state 0. That's this line right there. If I'm in state 0 and D is low, I go to state 1. That's this guy right here. It's low, go over to state 1. Okay? If I'm in state 1 and D is high, go to state 2. If I'm in state 1 and D is low, stay in state 1. If I'm in state 2 and D is high, go to state 3. If I'm in state 2 and D is low, go into state 1. So this is not like our counter. These two states up here are similar to counters, or D is sort of an enable, but this one is backwards, right? So don't just make the argument that this is counting. In this case, if D is high, we don't do anything. If it's low, we go to the next state. In this case, if it's high, we go to the next state. If it's low, we stay here, okay? This one, if D is high, we go to state 3. If it's low, we go to state 1. So no matter what, this state here, state 2, you can never stay in state 2 because that's this one here and there's no looper. There's no looper on this one either. You must go to some other state from either of these, okay? And in this code, you can see that's the case. No, again, no pun intended. I'm in 2, neither of these is 2. I'm in state 3, neither of these are 3. So this kind of a quick sanity check. Does it make sense based on our state diagram? Yes, in that regard. All right, so you can clearly see these values here directly mapping out of here. If you look at the state table up here, this should also match our Verilog values. And this is every one of these, right? Let me see if I can get all this on there at the same time. If I squish this, I can move that. Whoa! Move this over here like so. This state table should match our code exactly. So when state is double goose eggs here, up here, and D is, of course it's reversed, and D is 0, then that state should be 1, and that's this one right here, okay? And if the current state is 0 and D is a 1, the next state should be 0. That's up here, all right? And you can go down this table to make sure these are all the same. I'll leave that as a task in the viewer. There was an error in one of these when I recorded my class lecture. My TA noticed it and posted some dialogue, and it resulted in the last time I fixed this handout. Okay. What else? A quick sanity check here. I got, that's this one up here. 01 here. That's this one there, and a 11 there. Everywhere a moo. Old MacDonald had a farm. Yeah, this looks pretty good to me. Okay. All right, get this guy out of the way. All right, so that matches our state table, and here is our assigning of Q. We say in this case it's pretty simple. Q is true whenever the current state, which we store in SRAG, is 3. All right, so if the current state is 3, I'll put a 1, otherwise put a 0 in there. Plenty of ways to do this. You can simply assign Q in here as well. There's some people that argue, pro and con for that. The problem that I have with that is that in this case here, when I'm in state 3, I could simply say Q equals 1, like right here. And then maybe I could default Q equal to 0 up here, I suppose. Oops. You could do stuff like this, right? The problem with this is to me, this clutters up my code. It really depends on the complexity of your state machine. I'd rather not do this because, it's subtle. I suppose you could put Q in every one of these. I can't even do this, by the way, because I'd have to put a begin here and an end down there. Then the thing's starting to get all crapped up. I don't like this. No. Got to keep that one gone, by the way. I prefer this. Calculate the next state here, calculate the output over there. And one of the nice things about this, especially if you're dealing with a more style state machine, is, if you look at the diagram up here of what the definition of a more is, combo circuit, you've got your flip-flop, your latch, right, to hold the current state, and you have another combinational circuit over here, which may have nothing or something in it, and that directly generates your output. Well, if you do it this way, it's exactly what you're looking at. Here's your flip-flop latch that holds the current state, and the logic that dictates how it's going to get updated and when. Here's the combinational circuit that represents how you, ingest your input and you apply the current state, right? Current state here is in your case statement. The D input is here, and this is your S next, literally coming out here, okay? Down here, you've got your current state and your decision of what to do to create your output Q value. There's your current state, here's your Q. It matches this diagram perfectly. It's more, it works great. In a melee, we'll look at that in a minute. Is that down here? Somewhere down here, we'll look at the melee one. And I do the same thing in a melee as well. It doesn't exactly match the 3 boxes anymore, but logically it still does. Anyway, we'll take a closer look at that in a minute. But I really like this for more styles. It's right in your face, makes it real obvious, very simple. Quick gander at the test bench. We have actually 2 test benches in here. Now I added this second test bench after the class video and all that, and I modified the handout to add this second test bench. We'll look at the second one after we talk about the melee design, because it's kind of related to that. It's directly related to that. So what do I do in the test bench? I do the same sort of thing I did with the counter. I create a unit under test to connect up the inputs and the outputs. Well, what am I doing? I match the course handout. I initialize clock to 1 because the falling edge, the neg edge, is the active going edge of our clock. So it's upside down, so to speak. And in order to match the course handout with this timing delays and stuff in here, we need to start with it high, okay? So what do we got? Reset is off. We start with D of 0, and the Q is the output from this guy. And this is a true statement because D starts out low. It turns out my comment to start clock high is different than down here, which is low. But what's not shown in here is the test bench resets my state machine, which would be in the left edge of what we're looking at here. We'll see that in a minute when we plot it, okay? Free running clock. In the usual, save my stuff. Here's my resetting. I wait 2 ticks, which is 1 full period of our clock. We set the reset. We hold it on for 2 periods, right? 4 ticks, 2 periods of our clock. And we turn off the reset, and then what do? We turn on, set D to 0. And these are all 2. It looks like we got a 4 in here. Oh, that's because it goes 1 for 2 periods right there, okay? So you'll see that the D going up and down matches this diagram right here. And what we want to do is we want to see the D, or rather the Q output, go active after, I don't know, down here somewhere. It goes, 0 for 4, 1 for 2, and then it goes back down, 1 for 2. I don't know what I'm looking at here. D is 1 for a single cycle. Matches figure 5. While I'm looking at figure 3. Maybe that one's for figure 5 over here. What am I looking at? Is that the right test bench? Oh, it is. Yes, I'm sorry. This is a waveform that shows one single perfect data input that matches this message. And this is all true, and it works fine and dandy. This down here has some extra stuff going on. It has a false trigger here, obviously, and a false one there, followed by a 0 and a 1 and 1 there. So we could test more cases, all right? Sorry about that. That one matches figure 5, which is this one. And we can clearly see that there's a 0, 1, 1 that will be recognized here if it does it right, and another 0, 1, 1 if it recognizes it right here. And we can see that this waveform down here and the sequence of state values is more representative of a real test bench anyway, because it will allow us to test each one of these states and each one of these transitions. I did this all on purpose. It's my story, and I'm sticking. No, that really is why I did this. It recognizes a message here after garbage and so on, and this one here recognizes a message immediately after another message, and it, after recognizing the message, has a 1 that is retained on the D input. So in that case, I will have recognized the message in here, and I traverse back over here. All right, so that's why I had to do it twice. This one here recognizes a message followed by a 0, and there's the recognize a message followed by a 0, so that is that arc right there. So if you'll pause the video and look in here and count all these, there should be a coverage of each one of them, all right? And I go over that with as much pain in detail as I just did on the successful case that we just did in figure 3. So let's say I make plot this. This should be the test bench we just looked at, which is the first one, because that used to be the only one when I first designed this example app. Let's go ahead and make it fit. You can see, what do we got? Here's the queue. Let's make them in the same order as the handout. There's no reason that we have to be confused. You see the false one, Here's the right message in the queue, and another one here in the queue. So we've got them both. Let me see if I can get it all up on here at the same time. Oh, look at that. If we're really lucky, I can scale them to be the same size. Oh, not bad. Just by kind of guessing our way through here. So these all sort of line up. Actually, not bad at all, really. Yeah. Guessing our way through. All right, so you can see the reset here. The reset's high, and the reset goes off. So on this, what is it? This trailing edge right there, I reset my state machine so that when it wakes up, D is 0 and Q is 0 to match what happens in the initial state over here. In this handout, we didn't talk about resetting the thing, but if we're going to actually build one, we need to think about these things a little bit more than some academic lecture. All right, so in this case, we have a high going edge clock, and it's that one right there, right? And we got a low edge, and then we got another high edge. It lines up close enough. And what do we got here? We got the data. Wow. Here, boy, this is unfortunate. Come on. Let's scale this. If you kind of squeeze your screen around and then you kind of play around with the scaling and fit to scale buttons here, you kind of get it to fit. That's a little bit better. All right, so as we clock through here, we can see all this stuff lines up. The data goes high and low on the leading edges in this design, in this test bench, while the sensitive edges are the falling ones here, all right? I did this on purpose to guarantee, I explained this last time, that the D will never violate the setup and hold times around the clock if I make it visually so obvious that the D is changing nowhere near the active edges, okay, which are these here, okay? What else do we got here? So here it is going along its merry way, and it matches this diagram down here perfectly, which means either I was wrong when I made the handout and the Verilog is also wrong to match, that's a possibility, or they're both right. Or the best observation to make is that the Verilog implementation matches the reference, which is the handout. Right or wrong, they match, and that was the goal all along. Now, let's open this up. I think we did this last time, right? We looked at the state counter inside of the clock. If I could get the darn thing to open up. We can add these to our display here if we want to. And the value of doing so is, we can watch how the state, if it matches these or not. So this is the sreg, which is the current state. Let's take the next state and put it up here out of the way for a second. These numbers in here should match the ones down here is the point that I'm trying to make here. If I didn't squish it too much, is that still the right? Yeah, it looks pretty good. So what do we got here? We got a 1, which match. Oops. We got a 1 that matches the 1 here. Let me click on this. Scroll to the right. Now we got a 2, which matches this. We got. Helps if I put the mouse in the right spot. Okay, so we have a 2 here, which matches down here. Then we got a 1 followed by another 1. In this case, it doesn't transition, so it doesn't show that X like I showed in here. I could remove it from there because it doesn't really change. I left the X's in there because, by definition, it could change or it could glitch or something during that time. It won't, depending on your design. In our Verilog, it doesn't glitch at all. Down here, we see a state 2. That matches a state 1, and so on. So we can see it walking through these states, matching the diagram down here, which is pretty cool. All right, so this thing works out fine, just like the counter. The next state is based on the current state and the input. When we were counting, there was no input. It was just free running, or the enable input in the Verilog that we wrote last time was telling it whether it would advance the count or not. In this case, and we also see, I just moved the next waveform down here, we can see that based on the current state and the current input, the next state value, the S next value here, let's turn on our waveform highlighter here, okay, that says it should be state 2 unless something changes. And it is down here, state 2. Once I'm in state 2 and D is high, if it stays high, the next state should be 3. But it changes right there, and it says, oh no, because I'm now seeing a 0 if the clock, if the edge falls, I really want to stay in state 1 or go back to state 1 here. Which is the situation where I saw a 0 on that falling edge. I saw a 1. So I'm halfway, working my way through the message. And then I got a head fake, I guess, a glitch on the D signal. And I got a 0. Well, I don't want to, I didn't recognize a 0, 1, 1. I only got part of the way. So I got to go back to state 1 and say I just saw a 0 that might be part of a message. Okay? That's why this changes right in there, and you can see that it's combinational because X next is dependent on the current state value, which is 2, as well as the D input, and it changes whenever D changes, or I should say it can change whenever D changes. You saw that over here as well, okay, which is not necessarily changing on falling edges, okay? So this is a combinational circuit that inputs are the state and the D input. Okay, so this can move around as it does over the course of time. And the state only can change on the falling edge of the clock and lock it in. This is the hallmark of a Moore-style state machine. Okay? And this is how I implemented this one in Verilog. Now, let's look at this example here, a little foreshadowing. What happens if D glitches over the course of time while it is running? This will make more sense after we look at the Mealy state machine. So let's put a pin in this and come back to it in a minute, all right? So what is the difference? There's, by the way, if you want to implement it in a schematic form, there's your 138 type decoder, a couple of OR gates to determine what your next state is based on the sum of products up here. You have 2 bits in your next state, so you're going to have 2 sums of products, and that's why we have 2 OR gates down here. All right? This down here is the circuit that decides that I'm in state number 3, which can be done with an AND gate on the two outputs. So this down here is my always assignment, and this over here is the always that does the combinational stuff with the case statement in it, all right? Or you can do it this way with discrete gates if you want to. Remember a Mealy state machine. The output is defined by the current state and the current inputs. The Moore style was solely set up so that the current state and that alone defined the output. So this one allows this input to sneak around here, which you don't get to do on a Moore style machine. Okay, so what does that mean? Foreshadowing alert. It means that Mealys are more sensitive to these glitches, as we'll see in a minute. And I added that glitchy waveform that I showed you above there so that we can see it in contrast and the Moore versus the Mealy style designs, which I didn't have before. Probably a massive oversight when I was using this in my lectures. So one of the things you're going to notice about a Mealy state machine is that it can have fewer states than a Moore style state machine. I think I mentioned that last time. Therefore, this table has less cases in it. The sum of products is a little bit simplified, although in this particular case, the queue is more complicated by the fact you can actually see D in here, where you're not allowed to see D in the output combinational circuit in a Moore style state machine. It turns out that Mealy style state machines can quite often have fewer states in it than Moore style state machines. Therefore, in theory, you might have less circuitry to build, which is why these are very important to understand. Okay? You might say, oh, don't even bother with the Moore style state machines. Well, as we'll see, this has problems with glitches. Or more accurately, I say, it can have problems with glitches in its data input, where Moore will not. Okay? Mealy can also be problematic with setup and hold times when you pipeline these things all together. We'll look at that in future videos when we're building more sophisticated circuits that have more than one state machine in them at the same time. But when you can use one of these, and the constraints in your environment and your situation allows you to use one, it can allow you to use less circuitry, and that's why we want to know about them. So what does it mean? In this particular case, we have a different style state diagram. You'll notice the outputs in these denominator thingies are on the edges and not in the nodes of this diagram. In a Moore style state machine, you'll see the current state number in here, along with a slash in the output value, as defined solely based on the current state. In a Mealy, it's based on the current state and the input, therefore, that's where you see them. This edge leaving this state, representing the input of a 0, and the combination of those two represents my output. Okay, so this is why you draw a Mealy state machine with its outputs on the edges. In the Moore style state machines, you draw the outputs based on the state. Okay, so this is one of those things. So you just throw one of these up in a quiz for a student and say, what kind of state machine is this? And they're supposed to notice that that must be Mealy because the outputs are on the edges instead of in the states. Okay. What else we got going on here? We only have 3 in our Moore style state machine. We had 4 states. What happens in a Moore style state machine is you must have a state that solely represents when an output has a certain value. In our case, we have a single bit output that needed to be a 1 when it saw a message. So I had to create a state that represented the state where a message has been recognized. In a Mealy state machine, I have a state that says I saw the first 2 bits of a message. I don't need another state to represent I saw all 3, because when I have a state that says I just saw the first 2 bits and the input is the 1 that is supposed to be my third bit, that then can be this arc over here. This is why you get rid of some states sometimes in these Mealy machines. And that's when I see the output of a 1. All right, go ahead and look at my my other lecture on the differences between Moore and Mealy here, or there's another lecture I mentioned last time that's given by someone else I found on YouTube, and I purposely chose all the same example stuff that they have in this video here, so that if mine is no good, you might be able to get it out of there. Between the two of those, you should be able to understand what's going on. And here I'll leave that as a side project, okay? So, in a Mealy state machine that we want to convert to Verilog, we got these 3 states. The inputs and the outputs are specified up here. And here is a state diagram, the one we just saw above, a la Mealy style. And I threw in some more cause-effect arrows the other day because since the output is dependent on the state and the input, look what happens down here. Here's all these glitches some of the glitches I was talking about, all right? Anytime the state changes up here, or the input changes, I can actually see the output change in a Mealy style state machine. In a Moore state machine, the only time I can see the output change on Q is when the state changes. All right, so we have more to do here. But guess what else happens? And this is another big benefit of Mealy. A Mealy state machine, if you look closely, when it does recognize the message, it asserts Q 1 clock sooner than it would in a Moore style state machine. And again, that makes sense because in order for Moore to say I saw something, it has to move into the state that represents the I saw something state. Where the Mealy state machine asserts Q when it says, I'm about to see something that I want to recognize. See where this goes true here? The waveform below, the timing diagram below, it's the same one that's here, and you can see the Q shifts left 1 clock cycle in here, okay, when we look at the Mealy versus this one. So in this one, my point is when Q is high, it's on this, in here at time period number 16, it goes high, when this is transitioning low, okay? And I copied the top part of this diagram down here so we can do an apples to apples on it. Look what happens here. There's your 16. This one goes high at 14. So it's not that it recognizes it sooner. It's that it can tell you about it sooner. Because it doesn't really recognize it until this falling edge right here. Remember, by definition, it's the falling edge of that clock that defines when something is sampled. So what really happens is the fact that Q is high right here on this falling edge is what represents the output of our Mealy style state machine. It's not that Q is high here. Everything is synchronous. The output, you say, is synchronous to the falling edges of the clock. So it's the fact that D is high when this falls. And this arrow here represents the fact that when it falls, it transitions Q from a 1 to a 0. So if you're looking at Q, the setup time is observed, and it reacts to the falling edge and will go low after the falling edge has completed. There's not a lot of hold time on here, but there's enough. Okay, but on this falling edge, Q is true, then it goes back to false. So it turns out that on this edge right here, the Mealy machine expresses the fact that it saw a 0, followed by a 1, followed by a 1. And I drew this arrow here representing the fact that Q actually goes from 0 to a 1 because in state 2 here, which is this one there, when the input is 1, as it is right here, that's what dictates the output being 1. So that matches this line right here, okay? So, point is, Mealy can give you this Q 1 clock period sooner than a more state machine does. Remember up here in the more, Q goes from 0 to 1 at that point, but it does it in response to this falling edge. So the setup time on Q, it's low. The hold time is low because on this falling edge, Q reacts to the state having changed. So Q is low on this falling edge here, and it is high on the falling edge here. I should have drawn another arrow right there. Okay? Then it goes low. Alrighty. So how do we do this in Verilog? We do the same sort of a thing. We create a combinational circuit that represents the calculation of the next state. And in this case, it's going to be the current state and the D input. And when we generate the combo circuit that represents our output, we have as inputs more than just the state. We also have the D input involved. That's why this expression there in equation 10 is different than the expression up here in equation 7. Okay? All right, let's look at then what's going on with that. That's going to be FSM4. Well, I'm covering a lot of stuff here, a lot of review. Sorry about that. And this has also got the stale link in there. What do we got going on here? Up here will be basically the same sort of thing. We got our clock reset D and Q. We got an SREG and an S next, representing the next state, current state. We got the usual always block here. I can go ahead and remove this stuff. I'm going to make that the same, quite literally. And then we get interesting over here. We have less states to worry about, and that matches our state table. Here we'll see, right? Less in here, less in here. What do we got? I'll talk about that in a minute. And we then should have a combo circuit down here. Now, I could have done this if I wanted to. I decided to go ahead and use a third always block to determine when Q is a 1 versus a 0. This is a lot of visual noise. I would do this myself rather than this big mess up here. I included the big mess as an example because sometimes the output is way more complicated than one simple little I'm in this state and D is 1, make Q 1, which is what you really want to have, okay? This is probably the right answer. But I wanted to make sure everybody understands that an assignment statement is really a combinational circuit. Anyway, you could have done it far more verbosely like this. And in this example, that's what I've got. I do that because some state machines are more complicated, and you might need to do this. And just, plant that seed, make sure you understand that there's no reason you couldn't do it that way. And as I said before, I could also put else's and other junk in here and make this one have more stuff in it too if I really wanted to. So what do we got going on here? The issue is we have fewer states. Therefore, there's less to do in here. Otherwise, you're doing the same task we did before. And people might ask, hey, what happens if SREG has 3 in it? Well, the answer is, well, that's the same situation or the same kind of question of asking, what if all the memory in my computer changes its values when I'm not looking? I don't design for that. Okay? Nobody does. If your hardware lies to you, you're SOL. It's not going to work. All right? So this is not something that that requires you to really freak out about this stuff. Certainly not in the hobby world. As other people point out, you may need to deal with stuff in, in medical situations or space probes and things like that in order to design for the critically detailed test cases that they have for that kind of circuitry. You may need to put in all those extra cases. I'm not doing that as a hobby, so I'm not that concerned. You certainly wouldn't use a lattice chip like this one in a spaceship. You may have other kinds of circuitry that have, parity checking and other kinds of special error correction and detection logic in it and so on, if that were the case. If you did want it to be thorough, you could just put in the extra cases in here and treat them the same way as you would a reset. If I'm ever in a bad state, I could then just simply say S next equals 0, which would be the same thing as I'm in a screwed up situation, reset myself. Of course, you then have to ask the question, what happens if this thing resets itself when no one is expecting it to be reset? Okay, again, if your memory doesn't work, then nothing is going to work. So I'm not going to worry about that particular case. Okay, so we don't go there. What do we see here? Same code on the thing. If D is high, we go. In this case, we're not doing anything. We stay where we're at. Otherwise, we go into state 1 and so on. These values, like I said, will match this. They will match this down here as well. We got state 0 moving around as it recognizes the message, just like before. Same message, a 0, 1, 1. We see the 0 is our input here, and it's changing state. We see a 1, and it's changing state, and we see another 1, and it's changing state again. So you can see that the message is hiding in these transitions here. We can see if the message is being recognized over the course of time, but then it's not the message. We divert to another place in our state machine. It says recover, because we started recognizing something, which is the state over here, followed by, it can't be that. It must be something else, so go back and start, partially restart, or I saw the whole thing and I fully restart, that sort of thing, okay? All right, so these glitches here are a fact of life in a mealy state machine, because D, in part, is what defines Q. All right, it's as simple as that. If I'm in this state over here and D is a 1, which by definition, D is a 1 to get into this state, D is going to have some amount of hold time on it in a real circuit. So when I'm in this state, even if D becomes 0 and I end up over there, it is a 1 for a short period of time. By definition, before it changes, if it does. So it will think it's going to go over here, and it will output this 1, even if it's just a little glitch. This happens all the time in a mealy style state machine, okay? So I drew these arrows in here to represent the fact that this thing does go high because it was sampled high during that falling edge. This is also debatable. Does the cause effect go from here down, from there down? Do I draw both of them? I don't know. Leave a comment below. What's your preference on this? Anyway, Q will glitch, is my point. So let's go ahead and run the test case. And see what happens here. Oops, if I can click this the right number of times and go like that and hit append and order them in a sane fashion. Here's my D and my Q, scale it to fit, and we can see what's going on there. And here is this guy up here. You can get it all on the screen at once, maybe, and scale to fit, maybe, ish. All right, so you see these guys working here, and they all match. Everybody's happy. This matches it perfectly. We come out of reset. We're low on the D input. Okay, D input goes high. That leading edge right there. I'm gonna line this up a little better. And we see what? I can put my current state, my next state up there. Let's go ahead and open this up. And we can sneak an eyeball. Let's put this one in here first before we clutter it up too much. All right, what's going on in here? We see all these numbers here should match down here. This is a state 2. Let's get that all lined up. We scale it right. This always takes 15 minutes. I don't want to waste our time. There we go. Close enough. We see D going high while I'm in state 1. I am in then state 2 right there with my little glitch. We can see all this lines up and matches perfectly. Woohoo! All right, this is pretty nifty. And to finish the more academic side of the discussion, if we add the next state, we can see this next state changing and going up and down as D changes, just like we did in the Moore style state machine. But the big difference here is that, since D is defined as not just a function of the current state, it is also a function, of D. All right, it glitches in here. All right, so that's the big deal. And the glitches are going to be our setup and hold nightmares if we don't do it right. Okay, so this is really more about how do you get Verilog out of this thing rather than how to do state machines in theory. But let's go ahead and look at this other glitchy example as well. I threw some arrows in here to emphasize the fact that D is going high and low in here, even in the situation where the message has been recognized, as is given by the case that Q is high at the point in time where this thing falls, right? As it is over here as well. It even glitches in the case when the message is being recognized, but it has glitches in the middle of the message. Glitches, that is, on the data line that are not coincident with the points in time when D is being sampled. If it glitches in between these falling edges, it's a tree that falls in the forest that no one's around to hear it, right? So to speak. Because recognizing a message is formally defined as a sampling a low, followed by a high, followed by a high. Period. If it glitches in between, we ignore those. We don't see those. And here is an example of it glitching when no one's looking, because I'm in state 1. And in state 1, over here, no matter what, I'm outputting a 0. But if I'm in state 2, and D glitches, I'm either outputting a 0 or a 1, depending on the value of D. All right, again, this is the whole hallmark of Mealy-style state machines. All right, so we got this. Let's see if it gets modeled correctly. I don't remember what what is it, plot 2? Plot 2. Woohoo! Scale that baby. You can see the glitches right there. I'm not going to mess around scaling this for 20 minutes. But you can definitely see that if D, where is it? Q goes on the bottom. To match the handout, if D glitches, Q over here can glitch if I am in the right state. In that case, I believe it was state 2. Where's my handout here? See this guy down here? State 2. And here, presumably, I'm in state 2. You can come over here, blah, 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 grab the current state. You can even grab the next state. The next state should glitch too here. Look at that. If we zoom in a little bit. Because D is changing, the next state combinational circuit will glitch. It can, I should say, glitch along with it. So this is generating a lot of noise, okay, all over the place. It'll glitch in the Moore style state machine on the next state as well. But the Moore state will never glitch its actual state, and therefore it'll never glitch its output, even if there's glitches in the data input, unlike the Mealy, okay? And that is this one right over there. I'm going to get these lined up the same way as the handout so we're not too disoriented. There we go, right? So the D has glitches when no one's looking, it's okay. If the D has glitches when we are looking, then we got glitches on the output. We always glitch the output on Q whenever we're about to finish a sequence. If you're doing a recognizer style state machine in a melee design, because of just sample and hold time, it will glitch. These glitches are just a fact of life with a melee design. So when you use a melee design when the glitches don't matter. Whatever's taking this Q value downstream, if they're only monitoring the value when the clock falls, all right? And keep in mind that Q changes its value, as I said before, after the clock falls. Okay? It's not high, then the clock falls. You got to be careful about this. Make sure your test benches, your test cases, do the right thing in the right order. This gets us back to the non-blocking assignments and all the other fun stuff that goes into designing Verilog programs. And that's why it's absolutely critical in this design that you use non-blocking assignments in here. If you can't make that quantum leap in your head, take a moment, work it out in your head. Why do we need... The most important one is right there. Why does that have to be non-blocking? Okay? The answer is because this has to happen after everything else in here settles down. In simulation, that is, okay? So that the current state is not updated until after all the combinational stuff here and news flash and all the combinational stuff on our test bench has settled down in the current simulation point in time, all right? So the only difference in these test benches versus the Moore style ones is I've got a lot more crud going on with a bunch of glitches and stuff in there, all right? But other than that, they're the same thing. And that pretty much wraps it up. These two, FSM3 and FSM4, have the glitches in their second test benches. And the melee style state machine, those glitches can get reproduced in the output of your state machine. And in the Moore style state machine, see these glitches here and in there, they will not get reproduced or propagated, I should say, into the output of your design. And the reason is plain and simple, the fact that your Q output is asserted after the fact. There's no combinational pathway for the D input to be connected to the Q. It's as simple as that. And therefore, you're not going to see these glitches appearing on the Q. Q isn't going to glitch all over the place like it does in the melee over here either. Q is very clean here. Problem can be, the Q happens one clock period later than it does in the melee. Since the Q goes active in the melee here, that's why these glitches showed up in the melee design. It doesn't go active until it's over there in the Moore, in which case the glitches will have been processed and ignored by the time Q goes active. And again, if we open this up and we look at our state and our state next, you'll see the glitches in here. All right, that's why I wanted to go back over here. If we didn't do this, look at it before. Those are your glitches on the D, and you can see them affecting, in this case, the calculations for the next state. But because they're all done and settled down before the next state is updated, it never shows up in the actual state. And if it's not in the actual state, it cannot appear in Q. All right? Again, in the Moore style design. All right, so I'm jumping all over the place between Verilog and basic FSM theory stuff here. I hope I got enough of the bases covered, especially if you're just getting started into this and you haven't really messed around with state machines that much, or at least formal ones like this. Hopefully there's enough of this that'll start sticking together as we then move on to design an actual UART or SPI and things like that, which is the next thing down the pike. So what do? How do you make real useful things out of this? Well, you use state machines. Right? These are a big deal. And we need to decide when we want one versus the other, and when we can tolerate the extra delay in generating queue or the glitches when we want the queue earlier with the two different styles. And enough to be starting to tinker with this if you want to try to make a UART, okay? We'll get increasingly waist deep into this stuff as we go, and maybe we'll hook these together and make some multi-state machine designs and do some cool stuff. Thanks for watching. I'll see you next time.